Okay, in this video, we will talk about the second regression model, which is called logistic regression. It's first proposed by the famous statistician David Cox in 1958. So logistic regression is picks the logistic regression function. So 3. In other words, the regression function looks like logistic transformations of the linear regression format. So which is S Wx plus alpha. Okay, where this S T is given by logistic form 1/1 plus e to the power negative t. Okay, and the loss function we pick the C, so which is a logistic regression loss. I will rewrite here. Logistic regression loss is given by the negative y times natural log z, 1 minus y, natural log 1 minus z. So logistic regression loss is negative y natural log z minus 1 minus y natural log 1 minus z. But this, although this has negative signs here, but actually these terms are positive because usually when we apply the logistic regression, the z is a number between 0 and 1. So if you take the log between 0 and 1, you get a negative value. So both terms are actually positive. Okay, so the cost function, we still pick the average square loss. Okay, so this in general, logistic regression can be used for two purposes. One is fits the probabilities with actually that means you have the y values between 0 and 1. Okay, but more generally, more popular case is usually is used for classification. So this is a little bit different with the QDA for the same purpose, but a different approach, QDA and LDA. For the QDA and LDA, these two models are generative models. In other words, it gives you the whole spectrum of the posterior decision boundaries. You can pick the decision boundaries with posterior classification probability equal to 0.5, 0.2, 0.1. But logistic regression it's a discriminative model. Which means you do not need to specify the prior probabilities and the posterior probabilities. It will so the posterior, so you do not need to fit the posterior probability distributions. In other words, do you recall that in the QDA and LDA we fit the normal distributions models separately for each class, and then we find the decision functions, and then we apply to the logistic transformation to find the decision boundary. But here, logistic regression, we just skip the fitting the normal distribution and fit the logistic function directly to the data. What we get is a fitted decision curve. Okay, so that's the differences between the two methods. Also, so now we know the logistic regression, we pick the regression function and the loss function. So now we can write down the cost function. Okay, here we denote the cost function equal to G, which is equals to the average squared loss of the logistic regression. Logistic regression can be written as a logistic function xi times w. We assume the intercept, the design matrix has 1 inside, so this model do have the intercept with yi. Okay, I from 1 to n, which can be written as summation. So we take the negative sign out. I from 1 to n. So we take this loss, right? So we average the loss. So it's negative yi natural log s xi dot product with w plus 1 minus yi natural log 1 minus s x I w. Okay, so what we need here is we find a w, the parameters in the logistic regression that minimize the following loss function. Logistic regression doesn't have the closed form solution like the like the linear regression. We have to use some numerical methods to find the solution. But now let's see what's the loss function looks like. For example, this is the loss function when the true label is at 0. Okay, you have a big loss if you give if the true label is 0, we give big loss at 1, right? If you predict as 1. On the other hand, if you want to check the loss function when the true label is 1, what's your loss function looks like? This will looks like decreasing up to 0. So in other words, if the true label is 1, we give very big loss at if we predict as 0. Okay. And for the probabilities, if you check the loss at 0.7, we can see the minimizer is actually here. So 0.7. So now we need to apply some because there's no closed form solution. So we can solve by gradient descent or stochastic gradient descent algorithm. So it can be shown for logistic regression, the GW, the cost function is a convex function. Okay, and then we need to find the gradient. Note that this function has a composition of two functions, has this S functions. So to make this gradient search problem easier, we can find the gradient of the logistic functions first. So what is the gradient of the derivative of the logistic function? Okay, so this is just 1 over 1 minus e to the power negative t. Okay, because by using the quotient rule, we know it's 1 minus e to the power negative t square, and the derivative, the bottom part, is just e to the power negative t. Okay, actually this can be rewritten as the st multiply 1 minus st. So the derivative, so on the left hand side, this is a logistic transformation, and on the right hand side, this is the derivative of the sx, logistic function x. And now we can find the gradient of the loss function, because when we apply the gradient descent algorithm, we need to, if we have the closed form for the derivative, it will speed up the calculation. So this will equals to, so derivative of this function will equals to negative summation. Let's see which term has w. So the first term has w, so yi is constant, yi. And take the derivative of the log. So you go to the bottom. So here, let's denote si equals to, si equals to this. This denotes si. Okay, so this denotes by the Fisher transformation, logistic transformation xi w. Okay, and then you take the gradient with si, with w. Okay, and minus 1 minus si, 1 minus yi, gradient si. Okay, so if you take a look at this term, you take a derivative this part, 1 over, you flip it, and then you take the gradient of the inside function by applying the chain rule. And this will equals to negative summation, because now we know both term has gradient, right? We can take the gradient term out. So we have the si minus 1 minus yi, 1 minus si. Gradient of the si. Gradient of si equals to this, right? Gradient is this equals to si 1 minus si. And then you need to take the derivative of the inside function. It's vector xi. Actually, after few algebra, you can, for example, this term, if you multiply them together, this term cancels this one, you will have a very simplified notation which is given by summation yi minus si xi. Okay, you just multiply this term to each of these two terms, and then you combine the terms, you get this one, and this will equals to negative xi transform yi. If we use the matrix notation here, let me rewrite this part. So we have negative x transform y subtract s x omega. Okay, where this we know this is design matrix transform. This is the label vector, and s x w is just a vector 2. Is s x1 omega s xn omega. Okay, so you just apply this s function component wise to the xw, and then once we solve the gradient descent rule, just you starting with some starting point w, you substitute w each step with w plus the learning rate epsilon times the x transpose. You apply this one to here. Y subtract s x w. Okay, so that's the gradient descent rule, and we also have the stochastic gradient descent rule. Suppose you have for the large data set, big data. Okay, if it's hard to calculate this as a whole, you can also update the algorithm by point, which means the stochastic gradient descent. In other words, you search W by point wise, yi subtract s xi w xi. Okay. So, and this stochastic gradient descent algorithm, we call it SGD. Okay, SGD works best if we shuffle points in random order. And process one by one. And for the big sample size, sometimes it even converges before we visit all the points. Here, I just give you one example. For example, this example, we have the classification of the red label and the blue label. Okay, and the logistic regression give us this decision boundary from the middle. Okay, if the points, sample points are linearly separable, this if you let the linear regression equal to 0, it separates them, because linear, if you check so because if you set the linear part function equal to 0, this gives us probability 0.5 here. Okay, this gives us the decision boundary. So that's how we find this middle part, line. Actually, scaling W to have the infinite length causes Sxi W converges to 1. Because it's logistic regression, so if you have the if you apply the W times Xi, if your W goes to infinity, okay, this will force this a point converge to label 1. If this Wxi goes to 0, this will classify this point as not in will be labeled as 0. Therefore, logistic regression. Furthermore, if you check the derivatives here, so if we make the Wxi increase to infinity or decrease to negative infinity, this will make the gradient goes to 0. Therefore, logistic regression always separate linear separable points. Okay, I think that's about the linear logistic regression. That's all I plan to cover today. Thank you.